that we've gone for offline, here we are. Okay, so we're going to work on this problem here. So we've got a triangle ABC defined by those points, which we see a nice sketch which hopefully helps us understand. So find the vectors A to B, B to C, and C to A, and the vector from A to B is B minus A. That's going to be okay. Now we've got a small issue here where I might have to scroll up and down, or maybe I can do this. Yeah. Okay. So let us go. We'll find A, B, etc. So the vector. Actually, what I'm going to have to do is look at this a bit off screen. Okay, we're back. So yeah, I have these off screen that I can look at. So the vector from A to B is equal to point A minus point A. Excuse me, point B minus point A. Now, the reason I write the lines underneath is to signify that they're not just numbers, they're actually a list of numbers, so they're points, okay? So I get 860. Now, if you have the manual in front of you, you'll be able to see that 860. I'm looking at it off screen. Minus A, which is 210. And it will be a vector, so it'll have three components. 8 minus 2 is 6. 6 minus 1 is 5. 0 minus 0 is 0. And you can nearly just see that from the picture if you look at it. How do you get from A to B? You go across 6 in the X, across 5 in the Y, but you don't go up at all. So the next one that we're interested in is the vector B to C, which will be C minus B. So C is equal to 754 minus B is 860. And so I get 7 minus 8 is minus 1. 5 minus 6 is minus 1. And 4 minus 0 is 4. And finally, we're looking at C to A. Excuse me. So A is 210. And C is 754. Equal to 2 minus 7 is minus 5. 1 minus 5 is minus 4, and 0 minus 4 is minus 4. Okay, so check your answer by showing that these vectors form a triangle. Now, what we'll do here is, now remember, of course, in this video, it's going to be quicker than a live one, so you should have plenty of time to pause me and rewind me if there's anything of any difficulty. So the thing about this we're saying is that if you go from A to B, and then from B to C, and then from C to A as a vector, that's doing nothing. And the length is nothing. And this is probably showing that this will show, well, yeah. So the length of a sum of vectors, say in this case, A to B plus B to C plus C to A is not equal to the sum of the lengths. It's only is when they are parallel. So that's a mistake not to make. If you're asked to find the length of a vector, you can't find the sum of vectors or a difference. You can't find the length separately. Because in fact here, this vector here, the length of this is 0. Now in fact, what you can say, we have a triangle inequality which says that the length of a sum of vectors has to be less than or equal to the sum of the constituent vectors. And that's fine because you're getting 0 on the left-hand side and something positive on the right-hand side. Now, okay, so we want to just basically check your answer. Now, it's very easy to see the answer if you look at this, because you've got B minus B is 0, A minus A is 0, and C minus C is 0, but we'll just do it carefully here. So vector AB plus BC plus CA is equal to, and if we look at these, so it'll be 6 minus 1 minus 5 is 0, 5 minus 1 minus 4 is 0, and 0 plus 4 minus 4 is 0, as it's supposed to be. Okay, let's see part C. Find the lengths of the sides of the triangle. Now, I really haven't given myself much space here, but I really haven't. So I'm just gonna just make a mark for myself. Space. I edit the manuals every year, try and make them better. Okay, so the lengths of the sides of the triangle. So the triangles, the lengths of them is the same as the length of the vectors. So if I want to find the length of the side BC, I just find the length of the vector from B to C. So all I have to do is find the length of these three vectors here, and they'll be the lengths that I'm interested in. So I'm going to have to do little Pythagoras here. I haven't got much space, so I'm going to kind of do it in my head. So remember, it's square root sum of the squares. So the length of AB is equal to the length of the vector A to B. Square root sum of the squares, I get, well, I have a little handy calculator here. Square root of 6 squared, which is 36, plus 5 squared is 25. I get square root of 61. And similarly, the length of BC is the length of the vector B to C, which is square root sum of the squares minus 1 squared, which is plus 1, plus minus 1 squared, which is another plus 1, plus 4 squared, giving me the square root of 18. And finally, the length of CA, and I have a bit of space here, so I'll use it, is the length of the vector C to A. So I do Pythagoras on C to A, square root minus 5 squared. If you're going into the calculator and you have negatives, you need these brackets, or else you can actually change them to positive for the purposes of calculating length, plus minus 4 squared, because, for example, 4 squared is the same as minus 4 squared. That'll be like 25, 36, let's see, square root of 25 plus 32, I get square root of 57. Okay, and so square root of 61, 18, 57. 61, 18, 57. 61. Now that looks a bit out of proportion, but if you actually look at square roots, say square root of 61, it's like it's about 8, and square root of 18, it's about 4. So it's not as bad as it looks. It's just near its whole number. So because otherwise it looks a bit out of kilter, but it's not. Okay, so we have the side lengths. What's the third question? Find carefully, now the careful is very, very important here, the triangle BAC. Okay, so we identified the last day, so you got BAC. Now what we have with the dot product, which I think I'm going to write down here, I'll write it up here. We have, if you want to find the angle between two vectors, you use this. So a vector U dot product, scalar product of vector V, which is easy to calculate, is equal to length of U, easy to calculate, length of V, easy to calculate, cos of the angle in between. Now, if you look at the angle theta here, now you have to draw a picture with this. So the two vectors, if you want to find the angle in between, they have to be kind of coming out of the same point, as it were. But if you look at this, like what vector is the angle theta between? Now you've got the vector A to B. And it's also between the vector A to C. Now you haven't got the vector A to C. Okay, so it's between AC and AB. We'll write that down here. So the angle is between two vectors, A to C and A to B. Now the mistake, and the reason I put in the word carefully here, is that if you do it, instead of between A to B and A to C, but you use the one you have C to A, you end up, if you did that, so the vector C to A, if you just move that to come out of the same place, it looks something like this. So what you'll actually find if you're not careful, so this is the vector in between C to A and A to B, alpha is actually 180 degrees minus what you're looking for. So that's why I said you have to be careful there. It's the angle between A to C, which is going this A to C and A to B. Now we might write down something here that's also useful. and it is the vector from A to C that we're interested in here is in fact in the opposite direction of C to A, but it has the same length, so it is minus C to A. You could use that if you wanted, but I think we're just going to find A to C ourselves. So we're going to find A to C directly. Let's see, we have space down the bottom here. There's no space, so A to C is equal to the vector C minus A. C is 754. Minus A is 210. 7 minus 2 is 5. 5 minus 1 is 4. 4 minus 0 is 4. And notice that it is indeed minus C to A. So this is the same as minus A to C. So look, they're negatives of each other. So we've got two vectors there. I'm just going to write them down for myself off screen. So the vector A to B is 650. And the vector A to C is 544. And we know that the angle in between those two vectors is the angle BAC, which is what we're looking for. There's a nice room up the side. So, now one thing we're saying here is that the length of A to C is definitely the same as length of C to A, root 57, which we found already. So what we're going to use is that dot product thing up here in red. The dot product of two vectors is the length of the first, length of the second, the cost of the angle in between. We find that AC dot product vector from A to B equal to length of AC, which we could find, but it's the same as length of C to A, which is root 57. Length of A to B, which we can go over and find in a moment. I think I'm going to write it down quicker enough. Square root of 61, I think. Just double that. So 636. Yeah. Times the cost of the angle in between. And the angle in between is what we are very much interested in. So we're going to find the dot product. That's going to be easy. We've already found the length of A to C. We've already found the length of A to B. So we'll have an equation in theta. So let's do this dot product. So the vector from A to C is 650. Dot product, the vector from A to B, sorry, that's not correct. A to C is 544. AB is 650. And remember how you do dot product, it's very easy, but you get a number, not a vector. So it's 5 by 6 is 30 plus, so it's a number, not a vector. So you add these. 4 by 5 is 20. And then one thing that people get caught out at, so 4 by 0. So if you think of 0 as nothing, you're going to make mistakes because 4 by nothing is 4, but 4 by 0 is 0. And so we end up here with 50. Okay, so if we're going to put all the information into that equation, therefore we have 50, the dot product of AC and AB is equal to length of AC, which is square root of 57. Length of AB, which we found on the previous page to be root 61. Oh my god, sorry. Tired baby was going nuts last night. No, sorry, I was right the first time. So yeah, times cos of the angle that we're looking for. Now, you're trying to solve this for theta. The first thing you want to do is get rid of this. So you've got cos theta multiple. Now the thing in the yellow is just a number after all. So cos theta is multiplied by that number. If you divide the right hand side by that number, you'll just have cos theta. And if you have two things equal and you both divide them by the same thing, so I'm dividing by the yellow thing, root 57 by root 61 on both sides, I'll have cos theta on its own. So I end up at 50 divided by root 57 by root 61 is equal to cos of theta. Now what you have to get rid of is this cos function. And just like the inverse of multiplying by root 57, root 61 is dividing, the inverse of cos is what's called cos inverse, which is a well-defined function, and it can be done by your calculator. So cos inverse of both sides. So you get, now equality is symmetric, so I'm going to end up with theta on the right hand side, but I can just put it on the left hand side instead. So cos inverse gets rid of the cos, and you get cos inverse 50 over root 57 root 61. Now that's the exact answer. We'll see, does the question look for so many? No, it doesn't look for any kind of, nearest to any degree or anything like that. So what I'll recommend is 4 significant figures. We can be in degrees here. So I got 50 divided by root 57 by root 61, and it comes out to be 32.01 degrees. Okay, let's look at this final question. It says, determine if the triangle is right angled at B. Now, in fact, it's quite easy to see this. If you do a little, I think I've written something that's wrong here on the next page. So if you look at the diagram, AB is in the XY plane and perpendicular to XY plane is parallel to K. That's not true. That is not true. That's wrong. So what I was trying to say, and I'm wrong here, is that for this to be perpendicular, it has to go straight up. But of course it doesn't. So like if you have a vector there in space, so just going along like that. So imagine that's on the ground. It's true that if you go directly up that you're perpendicular, but you don't have to go directly up. You could, like, imagine the corner of the wall. You can also go off. There's multiple ways of getting right angles between vectors perpendicular to that. So there's loads of ways. So that is actually nonsense. So the best way to kind of answer this, if it's to be perpendicular at B, you'll need that the vectors BC and AB are perpendicular. So the way that this angle here could be perpendicular, now you can frame it different ways. So you could say the angle between AB and BC has to be 90 degrees, but it's easy to see that the only way really that this can be right angled is if AB and BC are perpendicular. So maybe I'll just write down, if that's not convincing to you, I'll describe the other way of doing it. So if you're not happy with that, you can calculate the angle at B using, now you probably could use sine rules and cosine rules if you have them in your locker, but we'll try and focus on vector methods. So you could actually do that if what I'm saying is not convincing, because I wasn't convincing there. Right, so alternatively, let's look at AB.BC. So this is equal to AB is 650, and BC is, I don't have BC handy. BC is -1, -1, 4. So I'll do the dot product of these. So I get 6 by -1 is -6, plus 5 by -1 is -5, plus 0 by 4 is 0. That's equal to -11, and that's not equal to 0. And if it's not equal to 0, then they're not perpendicular. So AB, the vector AB, is not perpendicular to BC. So that means that that cannot be a right angle triangle, because the only way that could be a right angle triangle is if this vector coming out here like this is at 90 degrees with the vector C. Because if you've 90 degrees there, you've 90 degrees there, but it turns out because it's a negative dot product, that means that the vector here A to B and the vector B to C are kind of pulling apart, because remember that's what negative dot product means. So this angle here is actually bigger than 90 degrees, and that means that this is less than 90 degrees. It's not right angled. So that was tricky enough, I think, in fairness. So that's a fairly full example, and that's yeah, it's an important example.